you can trace some of the very interesting moments in the acceptance of black holes as real astrophysical objects back to Oppenheimer. Oppenheimer writes a paper with one of his collaborators in 1939. The paper is published, where he posits that black holes are going to be the death state of very massive stars when they run out of thermonuclear fuel, because the nuclear physics is not powerful enough to resist gravitational collapse. It was his most important pure science contribution, but he never really knew that. They published this paper. If you see the movie, there's a cute little moment, if you know what to look for, where they reference, Oppenheimer, nobody's going to pay attention to your paper because today the Nazis advanced on Poland.
Before we just started recording a minute ago, you and I were talking very briefly about all the philosophy episodes I've been doing today. And we also mentioned that there are some errors on your Wikipedia page, and this might come in a moment. But I spend a lot of time talking to philosophers. I've done lots of episodes with philosophers, and I often ask how it is that they got into philosophy. Mm-hmm. One of the top answers, I'd say number one is physics, number two is math, and then number three is religion. But I saw, and this could be where the error is, that in undergrad you also did philosophy.
That is true.
And so I'm wondering how it is that you got into physics and philosophy.
There's a lot of synergy here, because as we were coming up in the elevator, philosopher David Albert was coming out. David Albert was part of my shift from philosophy into physics. So I was an undergraduate studying philosophy, and I was so frustrated that we were still arguing about what Kant meant. It drove me crazy. Mm-hmm. And it was so personality-driven and so opinionated, and there were always the same people who really verbally dominated the classes. David Albert gave his job talk at Columbia, and he came into the philosophy department, and he spoke about relativity and connections to free will and causality and Einstein's theories, and I was so impressed, not just with his excellent talk, but with how quiet the room got. And nobody's arguing, what did Einstein mean by E equals mc squared? You know exactly what he meant. It's really a gift. It's something, physics is something you can share, and it's true for all of us. And once it belongs to you, you can share it with whomever. And I loved that. I thought it was real transcendent answers to hard questions, and that the answers were much more thrilling and much more universal.
I was terrified. Of course, you wouldn't have done this, but I was terrified you were going to say, David Albert scared me away from philosophy and into physics. But no, we just sat spellbound for a while, as I think for the first hour of the interview, he just gave this spontaneous lecture
about... It's a good talker.
Yeah, about time's arrows. And it was, of course, very physics informed and philosophy informed. How interested are you in philosophy today? Is that part of your work?
I'm sort of in denial about my interest in philosophy. I can be quite hard about, I don't want to do philosophy. I want to do physics. I want to follow the chalk. I want to calculate. And very much into the math and the calculation. I want to see the conclusion at the end of the day. I don't want to pontificate. So I can vocally be quite negative about philosophy. Apologies to my very brilliant colleagues and our mutual friend Sean Carroll. He makes fun of me for this, but you can hear it. I eventually drift around to some philosophical thinking. It's like I can't help myself. Mm-hmm. But I am very much attached to math and physics, and I think that the philosophy comes along. And I know a lot of people disagree with that. They think we simply don't understand some things and we have to tackle the philosophical questions. And I sort of feel the other way around.
Okay, interesting. I mean, there are certainly plenty of philosophers of physics, and not philosophers of physics, but philosophers just treading on physical territory that give philosophy of physics a bad name. So
yeah, there's some bad abstracts written out there, the prelude to a paper that are scandalously enraging. And it does kind of give that area a bad name. But there are important questions that are going to be picked up there.
Yeah, so
and resolved there.
before we moved on, I just wanted to say that I sympathize with you in this regard. And this is the last thing I'm going to say about David, though, is that we just did a pedagogically oriented episode on times arrows. I've been doing a lot of pedagogically oriented episodes lately. And for that reason, I could think of no better guest than you to talk with about black holes, given that the Black Hole Survival Guide has just recently come out. But I loved the cover art. The interior art was also terrific. It was fun to read, and it hit all of the great topics about black holes. So I really recommend that our readers check it out. Is there an audiobook too?
Yeah, I read the audiobook. Sometimes I forget these things.
Okay, that's awesome.
Yeah, so I did the audiobook. The art actually is a story. I have a collaborator, artist, Leah Halloran, and we did the work together. I really had it kind of sketched out what I wanted, and she did these beautiful large-scale paintings, and they're actually inverted in the book. She paints them. It's the dark to light is opposite in reality for these pieces.
And what I wanted to get to first then is black holes are obviously this mesmerizing aspect of astrophysics. But before we talk about black holes themselves, maybe it would be fun to talk a bit about the history of how they first emerged in physics before they were discovered.
Mm-hmm. Yeah. Well, you're right to distinguish black holes in astrophysics, because I think the fascinating thing about black holes is that they're somewhat fundamental to our theory of gravity, our current theory of gravity, and they can be made in other ways than just the astrophysical processes that we think of. There's something about black holes that is exceptional, and I think one of the most important, intriguing phenomena that we have to study fundamental law, and that's really unusual. You don't say that about anything else in astrophysics, really. So if you're asking about how they were discovered, when Einstein was struggling to write down a theory of gravitation, he was really struggling to write down a theory of a curved space-time in response to matter and energy. That's kind of how physics works. You say, here's the matter and energy, the sources in general relativity, and it will tell you how space-time curves or stretches or collapses, the dynamics of the space-time. And that's really kind of how physics works. In electromagnetism, you say, what are the charges? What are the currents? And that will tell you the electromagnetic fields as opposed to the gravitational field. He struggles to write this down correctly. It's a lot of false starts, and finally publishes the general theory of relativity as we now use it. It's 1516, and within 6 months, he gets a letter from an astronomer, a colleague he knows, Karl Schwarzschild, who has enlisted in the German infantry as a soldier on the, I think it's the Russian front, and between like calculating ballistics and strategizing about warfare, he's reading the proceedings of the Prussian Academy of Sciences, and he very deftly solves these equations for the curved space-time around a spherical mass. The thing that he does that's not odd to the mathematician or the physicist, but sounds odd physically, is he says, let's just idealize this. Instead of me trying to figure out how big this spherical mass is, I'm just going to imagine, just for fun, pretend, thought experiment, that I crush all the matter to a point. And I look at Einstein's equations for the curved space-time around this somewhat unrealistic scenario of crushing all the matter to a point. It's a beautiful mathematical solution. It's really quite sweet to teach it. It's only a few pages to go through how he comes to this conclusion. And what he solved for is what we now call the black hole. He didn't call it that. But it has all the features, all the hallmarks of this region of space where the curvature is so great that not even light can escape, which is what we mean by the event horizon. And it has all of the sort of typical features of a black hole. Now, Einstein's very impressed with this mathematical solution, and he helps Carl Schwarzschild get the work published. But he thinks, but this is a thought experiment. This is a fantasy. Nature will protect us from such crazy things as a singular, infinite curvature, infinite energy mass crushed to a point. After all, it's really hard to crush things. I mean, if you try to crush things, it's really hard. You can't even crush paper very effectively.
Right.
And so he rightly, to some extent, Einstein concludes, mass, once I put in the resistance of matter to compression, they just won't actually form in nature. But they're a lovely mathematical model. And he helped Schwarzschild get this published, although within 6 months, Schwarzschild dies from an infection that we suspect he contracted on the front in the war. So he doesn't live to see the importance of his legacy.
When you mention how difficult it is to crush paper, I just think about it for a moment, and it puts a black hole in a bit of perspective. I hope that this isn't too pedantic for you, but given that I don't want our listeners to have to know too much physics just to get into the conversation, one of the things that you mentioned right off the bat is the curvature of space-time.
Mm-hmm.
And most people, I imagine, don't really know what space-time is, and they certainly don't think of space as curved. So it would be interesting to hear
Absolutely
where that emerges.
It's you always see these kinds of confusing visualizations where it looks like there's this sort of deformity and some fabric and it points in a certain direction. Why is that direction special? So there are a lot of kind of misleading visualizations, but I can do curved space-time in a much simpler way without any of those complicated drawings. So it really takes two ingredients. The first is the concept of free fall. And this was something Einstein thought a lot about. Right now, I feel like I'm heavy in my seat. And so I mistake this for gravity. Or if I stand up, when we came up in the elevator, I really feel the elevator pressing against my feet. And I think that's gravity. But in both of these examples, there's really atoms in the way. Why do I need a chair or an elevator to talk about gravity? I shouldn't need anything. I should just have the earth far away from me. And so we can imagine in this thought experiment, and we're standing in the elevator, let's say we don't know how we got there, we can't see out, and we're in this box. If you cut the elevator cable, you're very high up, let's say, you will feel completely weightless. The floor of the elevator will fall away from you, and in fact, it will look to you like you're one of the astronauts in the International Space Station. I could take my water bottle and float it in front of me, and it would, because it's falling with me, look like it's falling freely or weightless. It looks like it's weightless. And this concept of when you are freely falling, you are experiencing gravity in its purest form. That weightlessness is gravity. That's somewhat counterintuitive to people. But you're experiencing gravity at its purest when you are falling weightlessly. Bad example, jumping off the top of the building. During the descent, you are experiencing gravity in its purest. There's no chair in your way. There's no elevator cab in your way. The unhappy end is when you interact with the earth, and that's atoms again. So that's the interaction of atoms and atoms. But the falling, that weightlessness is the experience of pure gravity. So now I'm going to combine that. Einstein called it the happiest thought of his life. I'm going to combine that idea of the weightlessness with regular observations. If I let things fall freely, I take that bottle of water and I throw it, it will follow a curve. And you could combine these two ideas and say, oh, the bottle is experiencing gravity at its purest when it is falling freely. And in that descent, it follows a curve. And in a simple couple of steps, I can come to the conclusion the space through which it's traveling is actually curved. And what the bottle is doing is it's falling along the natural curves in space. Now, it's not helpfully painted. I don't feel the curvature, but I can see it all the time from the way I can go around the globe, go to Australia, go to Indonesia, go to Texas, go anywhere in the world and throw things, and I will see the curves that they fall along. And I can paint a picture of what the space-time around it looks like in that sense.
Before or early in my undergraduate career, I did a stint as an astrophysics major. And there was one myth that was dispelled for me in one of the introductory astrophysics classes that I think if we can impart upon our listeners, this will, aside from everything else, make the episode a resounding success. And this is the idea that there is no gravity in space, and that when an astronaut is in the space station, there's no gravity.
Right.
So
Untrue.
So I'm wondering if you could explain what's happening when a satellite or an astronaut is in orbit and where gravity fits into this.
Yeah, that's exactly right. It's very much under the pull of gravity, for instance, the International Space Station. So what happens once they get the space station in a spot, they're putting themselves on a circular orbit around the Earth. And the way that they do this is they fire the rockets, they start going really fast, horizontal to the Earth's surface, and then they turn off their engines. And if they get the right speed, they'll just start falling. So they're literally falling towards the Earth at all times. They're just cruising so fast. It's like 17,500 miles an hour or something like that. They're cruising so fast that they just always clear the horizon, but they are in constant free fall. I've spoken to astronauts who have been on the International Space Station. I'm like, do you feel like you're falling? It's like, yeah, you can kind of psych yourself into feeling like you're constantly in this free fall. And it's the same example as jumping from the building or being in the cut cabled elevator. And so they're very much feeling gravity. If you were to stop the International Space Station from its cruising speed, it would drop to the Earth like a stone.
Yeah.
And that circle it's traveling along is precisely, I would, in this language, say it's one of the curves in space-time that it's tracing. It's falling along the natural curve in space-time. And that's really all we mean by the curves in space-time. We mean the paths that things fall along are curved. And in very, very far out space, where there really is no reference, you can't see planets or galaxies or something so far away from you, nothing's pulling on you, you will literally travel in a straight line. No more of these circles. And you might not even know you're traveling at all. There might be some sense of ambiguity if you're moving or not. But with the International Space Station, it is unambiguously cruising on this circular orbit around the Earth. And it's very important that they can turn off their engines because they are literally just falling. They don't need to be firing engines and burning fuel. That's how the whole space station works. If it had to be constantly firing its engines the way a plane does, it wouldn't be up there anymore.
That'd take a lot of fuel.
It'd take an unreasonable amount of fuel.
It would also, I imagine, take a lot of fuel to go from 17,500 miles per hour to a full stop. But that is interesting to think that suddenly it would just fall like a stone. It would fall
like a stone right to the Earth.
Yeah.
I mean, deorbiting satellites is a kind of a controversy. We leave a lot of junk up there. There are now tens of thousands of human-made satellites in orbit around the Earth, and they're just kind of in the way of other traffic, and they can be quite dangerous. And one of the things to decide when you launch a satellite into space is if you're going to build in the ability to deorbit that satellite and burn it up in the Earth's atmosphere and land it safely in the ocean or back on Earth, or if you're just going to leave it up there. I don't think they're going to deorbit the International Space Station. Don't actually.
Is it scheduled to be decommissioned anytime soon?
It's going to be decommissioned surprisingly soon. I'd say within 10 years.
Okay, wow. Is there...
Very surprising. I know. It's kind of
It's a staple.
Yeah, it's been such a significant international collaboration and cooperation. It's another thing I absolutely love about science versus philosophy. No offense to my philosophy colleagues. It doesn't matter where you're from. You can participate in international science experiments because the physics is all the same and the math is all the same. It doesn't matter your personal or religious philosophies. And the International Space Station, I think, was a wonderful example of global participation and peaceful collaboration. I mean, we are up there with Russian cosmonauts and Americans and other nationalities, and I think it's something to look at as an example of a better way for us to interact as nations.
Speaking of your interest or passion, I should say, in participation in science, we'll, of course, get back to this later in the conversation, but I have in mind your close involvement with pioneer works in Red Hook, Brooklyn, where participation in science is very important. But for right now, something else, or a couple things that you said earlier in the conversation, is you pointed out that even though I associated black holes with astrophysics, they're actually a very deep part of fundamental physics. That's one thing. The other thing is that you said that black holes can be formed in many ways.
Yeah.
And I think toward...
Well, we think.
Yeah, we
we
think.
only know of one way for sure.
Right. Theoretically, they can be formed in... I have in mind like wrapping strings and brains in various...
Or in the Big Bang as part of the primordial particles. You can make little microscopic black holes.
Yeah, but I just thought that toward introducing what black holes are...
Yeah.
Maybe we would
I think
start
that's
with
worth doing.
how fundamental they are.
Yeah, so you'll hear a description of one way to form a black hole, and that is the death state of a star. Very, very heavy stars that collapse under their own weight and cannot resist the complete gravitational collapse and become black holes. But that's not what a black hole is. So what is a black hole? A black hole is really, I like to say it's more of a place than a thing. It's a region of space-time that is so strongly curved around a mass, or what an equivalent gravitational mass, however it formed, that not even light can escape. And by that, in the spirit of talking about a curved space-time, I mean that the curved paths that light will fall along, even at its incredible speed. We talked about the speed of the International Space Station being over 17,000 miles an hour, and the speed of light is, I'm going to switch to kilometers, 300,000 kilometers a second. Even at that incredible speed, light gives the illusion of traveling on a straight line, but it also travels along a curved path in space. And that depends on the way matter and energy are distributed. So in the case of having a mass at some center in this kind of that distribution, if you get close enough with all that mass still concentrated at the center, there will be a point where the curved paths of light only lead inward, where there is no path for light to fall at its incredible speed outward, and we call that region the event horizon. And I think it's really important to say that's a place. Okay? Mm-hmm. It's a place in a space-time that is otherwise completely empty at the event horizon. There's no stuff there. There's no very dense matter. There's no remnant of a star. It is really a region and almost an archaeological record of something that happened to create that event horizon. And so I like to think of black holes as places more than they are things, although sometimes, they do act like things.
Your discussion first, or you mentioned light following curved paths, and then, of course, you mentioned how important light is to the event horizon of a black hole. I think it might be worth, since we began by discussing Einstein a bit, talking a bit about gravitational lensing and Eddington and what this phenomena is and how it was related to relativity.
Yeah, it's another wonderful story. It was 1919, I think, when Eddington led an expedition to witness an eclipse, and it was a total solar eclipse, which is just a very lucky accident that our moon happens to subtend the right size on the sky to completely occult our sun. That's just an accident, and in some very large number of years, it will spiral away from us a little bit and no longer be the case. So we'll no longer be total solar eclipses. So we joke, like, you have to do astronomy now, Now's the time, seize the day. So this total solar eclipse was very noteworthy to Eddington, one of the very early proponents of relativity, because it allowed him to make a very unusual measurement. He was looking at a star cluster that technically was behind the sun. Now, if the sun is blazing bright, you can't directly look through the blazing sunshine of the sun.
It's pretty bright.
It's pretty bright, this little star cluster. But if the moon helpfully occludes all of the starlight of the sun, you can see faint objects around the sun. Now, if relativity is right, the light traveling from the star cluster Some of it will go above the sun and around the sun because of the bending of the path of the light. The light won't just travel straight out like straight rays. It will actually follow curved paths around the sun into your telescope so that to you it looks like the star cluster has repositioned somewhere where it is not. And in other words, you're seeing behind the sun. And how are you seeing, if you make this observation, you're technically seeing something that is behind the sun. And how is that possible? It's possible because the path that the light follows is curved. And so Eddington set out this expedition. I believe he had a team in Brazil, and his team that he was with was off the coast of an island in Africa. And solar eclipses only last a few minutes. And initially there was rain and cloud cover, but a couple minutes into the eclipse, it breaks. They make this observation. They can see the star cluster. It's popped out magically from behind the sun, confirming Einstein's prediction of the bending of the path of light. There's some debate among historians of science how good the data was and how hopeful he was to make the observation. But the lesson is there that it was the first confirmed observation of Einstein's theory of curved spacetime, and it catapulted Einstein's fame in the English-speaking world. I also should say it was also a profound moment of a transcending nationalism and war, because this is just 6 months after the end of World War I, and Europe is decimated, and the British and the Germans, of course, were in this terrible conflict. And for an English scientist to confirm a German scientist's work was quite radical in its way. It was like quite a statement for him to do that. So Einstein becomes front page news, and it really marks a transition scientifically and I think culturally. Sometimes joke like they stepped out of the shadow of the war into the shadow of the moon.
That's interesting.
And and emerged as like cooperative citizens of the same Earth.
Yeah, I imagine that must have been such a remarkable moment to realize that experiment confirmed theory and showed that we lived in a radically different world than people had realized before Einstein.
Yeah, absolutely. And a much more radical picture than even Einstein realized. Einstein did not solve his equations to find the black hole. We just discussed that was found by somebody else. And he didn't solve his own equations to find the Big Bang. That was also found by other groups. And he was quite resistant to both of the ideas, not the math, but that nature would have such things in it. He resisted that interpretation, and of course, black holes are very much part of our reality, our astrophysical reality. We observe them; they're there. They're part of the functioning of our galaxy and the space that we live in.
And just to make sure that I have what was happening clear for our audience, the mass of the sun is sufficient that it is curving space, and then light is traveling following a geodesic, I think, so the shortest possible path between 2 points, and it arcs around the sun, traveling from behind it toward the viewer.
Yep, exactly. And the sun is not dense enough to create an event horizon, so the light escapes and it comes at us and it hits our telescope, but it's still a curved path. And if the sun were to collapse and get denser and denser, the path that the nearest light that's just barely skimming past the star will get tighter and tighter, and eventually you'll even find a circular orbit for the light, and when it gets small enough, the event horizon. So our sun's like 1.5 million kilometers across. If we wanted it to be a black hole, we'd have to make it 6 kilometers across, and that's where the event horizon would form. So it's a pretty radical compression, and it won't happen to our sun. Our sun will have a different death state in its future than the black hole.
You just said something that, all of this is very fascinating, but something particularly fascinating. Are you suggesting that just as the International Space Station orbits around the Earth, that there is light that is just sort of trapped in an orbit around black holes. It's just going and going.
Yeah, you can, just like they had to compute where's a good circular orbit for the International Space Station, to be on them. You can ask, are there any circular orbits for light itself? And there is one around every black hole just outside the event horizon, like just outside the event horizon. So when you start getting light so sharply curved, the path so sharply curved that you're making a circle, the event horizon's imminent. It's just inside that region. So I think it's like 3 times. So let's say, maybe like a radius of like 6 kilometers out or so, 12 kilometers across. That can be a circular orbit for a black hole sun. If it was our sun. It would be about 12 kilometers diameter, and the event horizon 6 kilometers. So they're really close to each other. You're talking about fitting inside Central Park, But so if you were to try to as you pass that orbit, you could shine a light beam, and it would go around, bounce off the back of your head, and then come back to your eyes. And you could see the back of your head.
Well, I know I'm getting a little bit ahead of myself here, but I just have a bit of a clarificatory question. So the radius of a black hole is directly connected to that black hole's mass. And because black holes are constantly accreting mass, the event horizon is consequently changing at all times. Does that mean that while in theory, if you had a black hole that remained of stable mass, there weren't quantum fluctuations around the event horizon, we might see light traveling around it indefinitely, but because...
It's delicate. It's hard to get it there.
Yeah.
I'll let you finish your question.
Yeah, but because it's constantly shifting the event horizon, there are all sorts of perturbations around the surface. You're probably not going to see light.
So I would say technically it's an unstable orbit, literally unstable, meaning a slight perturbation, and it's either going to fall into the black hole or escape out. And so the things like the International Space Station are on very stable orbits. You perturb them and they kind of tend to rock back to that very stable point. This is more like sitting on the top of a mountain. It's anything disturbs it slightly, it will fall into the black hole or come out. So you don't, but you do see things like rings, and you talked about gravitational lensing. Gravitational lensing is just the idea that there's a mass. It doesn't have to be spherical, it can be some crazy lumpy collection of galaxies or some other density. And you will see light shining from behind it will come around and you'll see it get lensed. And what you mean by that is it's bending the path of the light. It's just another language to describe the curved space-time. And you can see like entire arcs and things and really interesting geometric properties of the what's happening to the lensed light. Nobody's ever seen what we call the light ring. That's what that unstable photon orbit is called, the light ring. I mean, we haven't seen that yet, but it's around what people are looking at when they take the picture of the black hole recently in the past. That's just very recently. Was that 2019? Because I remember, I think it was the centenary of the Eddington Eclipse expedition, and it uses the same technology, which is to take the bending of light and to try to look for the light around a black hole that way. So we see effects that are very close in now. But I just want to address one question, which you said about the changing black hole. So some black holes are accreting a lot of material and changing all the time, but some are not. Some black holes are just out there by themselves. They're not harming anybody. Nothing's happening to them. They're not doing anything to anybody else. We don't see them if they don't do something. So I just literally have a dark. So the idea that light can't escape literally just means they go dark. I can see a shadow because it'll absorb all the light within the event horizon and allow you to see the light coming from outside. It's no different than the shadow of a tree. That shadow is really quite harmless, but we can try to look for the shadow, and that's what this Event Horizon Telescope did, is it took a picture of the shadow, essentially, of the event horizon. But some black holes are just dark against a dark sky. There's nothing to look at. And that's why detecting the collisions of those black holes by the ringing of space-time with the gravitational wave experiments was so thrilling because you're detecting black holes that are otherwise completely dark.
Thank you very much for clarifying my comment. Let me, though, ask or probe a bit further about this. I'm guessing that it is supermassive black holes at the center of galaxies that are, you can kind of count on them to be a center of a lot of activity, but then maybe stars that went supernova and then were ejected maybe by their solar system, or they already consumed everything around them and they're just kind of floating out there. They're the ones that they've got nothing going on.
Yeah, so there are a lot of star systems are born in pairs. There's a lot more binary star systems than there are single star systems. So we're kind of odd in that we just have our one sun. Not that odd, but Jupiter's almost a star. And so a lot of them are like, yeah, it could, I mean, it's not igniting, it's not burning thermonuclear fuel, but it's pretty big. And so it's not uncommon to have that two largish body, two that actually burn thermonuclear fuel or two stars. And if one of them dies as a black hole, it goes through its whole life cycle, it runs out of thermonuclear fuel, it begins to collapse because it's the thermonuclear reactions that are pushing the star outward and keeping this incredibly massive body from collapsing. And when that fuel turns off, it can be a very catastrophic event. And if it's massive enough, it will just completely collapse to a black hole. Might supernova in between. So it bounces, explodes out, a big outer atmosphere, becomes the brightest thing in the galaxy for a while. But the core, the remnant that's left after that supernova explosion, if it's massive enough, it will form a black hole. And those can be very bright because they can start to cannibalize their companions. So this neighboring star that they were just living and orbiting, much more complex orbit, it's hard to know if planets could exist stably around the binary star systems. But now you have this black hole, and it starts to, like cotton candy, it starts to tear off tufts of the other star, and that gets really bright. And that was the first indirect evidence of black holes that we saw, was this kind of X-ray energy coming out of this very, very tiny, tiny region of space. So if you estimated how much mass is in this tiny region of space, you deduced indirectly that you must have a black hole causing all that mayhem. And eventually it just completely cannibalizes its companion.
Yeah, intergalactic cannibalism.
Yeah.
Very exciting.
Yes,
phenomenon.
very exciting, right? But if it's not a binary star system, it's just a massive star by itself, it'll go dark. And if they both become black holes, which is what we definitely now can detect, these binary black hole systems, they're in orbit around each other, they're totally dark. There's just no light coming out.
Gravitational lensing was not actually something that I had anticipated that we would speak about at all, but I'm glad it came up, and it most recently came up when you mentioned how this photograph of black hole that, did you say maybe it was taken in 2019?
It was released in 2019. I mean, it was taken over a couple of years,
Yeah.
I guess
it required some new technology or developments in technology. I'm also pretty sure that along with these developments in technology, gravitational lensing has also been used for exoplanetary research. So for our listeners, these are planets orbiting around stars other than the sun, and perhaps even for learning about their atmospheres, but that I'm less sure about.
Mm-hmm.
Still, one thing that's very interesting about our discussion of gravitational lensing is Einstein had a theory that resulted this unexpected prediction, and then it was confirmed by Eddington's observations, and this had a dramatic impact on the community. What I'm wondering is what the analogous story is for black holes. My understanding is that when they were first predicted, or seemed to be a consequence of the theory, they weren't so readily accepted. So what was the story like?
Not at all. Absolutely. And again, it's reasonable to say, well, that's a lovely thought experiment and great imagination, but how are you going to crush matter to a point? I mean, it doesn't like to be crushed because there are internal matter forces that are competing with the gravitational collapse. And it's reasonable to believe that matter would win. I mean, my chair's not collapsing under its own gravity. Everything is gravitational attraction. I mean, technically, there's some gravitational pull between the atoms in here. It's very weak. Gravity's weak. very, very weak. So it's very easy to overcome it by just the atomic forces don't allow my chair to collapse into a black hole. And so that was a reasonable expectation. But the history is actually quite fascinating. You can trace some of the very interesting moments in the acceptance of black holes as real astrophysical objects back to Oppenheimer. Oppenheimer, like many of the scientists of the time, were genuinely just interested in nuclear physics. It wasn't solely to build nuclear weapons. It was because nuclear physics was just being understood. That was very interesting. They were starting to understand things about fission and fusion. And it does date back to Einstein because it's based in E equals mc squared, right? Einstein realizing that there is energy in just the rest mass of an atom that can be released either by fusion or fission. E equals mc squared energy is kind of behind the entire principle of making a nuclear weapon. That's the energy that you're trying to release. And it's tremendous. And it's like locked inside the atom. And people were just starting to understand the nuclear physics. And, nuclear physics is agnostic. It's not political. It's not about warfare. It just is. And so people like Oppenheimer, who were unbelievably broad in their understanding of things and, was very cultured, insightful person, was also interested in whether nuclear physics was the reason why stars shine. And back, that was work that was just being understood at around that same period of time. And they did begin to understand that there's basically thermonuclear bombs going off interior in these stars, and that's where all this energy is coming from. And they're unlocking that simultaneously in these defense programs, right, in the Manhattan Project. So Oppenheimer writes a paper with one of his collaborators in 1939. The paper is published, where they say, you know what? The nuclear physics that we understand now is not able to resist catastrophic gravitational collapse. It's a big surprise. He says black holes form. So in many ways, this paper, where he posits that black holes are going to be the death state of very massive stars when they run out of thermonuclear fuel because the nuclear physics is not powerful enough to resist gravitational collapse. It was his most important pure science contribution. But he never really knew that. They published this paper. If you see the movie, there's a cute little moment, if you know what to look for, where they reference, Oppenheimer, nobody's going to pay attention to your paper because today the Nazis advanced on Poland. So the paper is published the same day. The Nazis advanced on Poland, and it is not front page news that heavy stars might make black holes, and it kind of gets swept away with the whole climax of World War II and what happens to Oppenheimer in the aftermath. And John Wheeler, who was the granddaddy of relativity, actually gave Oppenheimer quite a bad time, said, this is ridiculous, you don't know what you're doing. You looked at too simple a situation, it was very idealized. And I guess there was a real professional split as well with Wheeler over this. And Wheeler was very powerful as a scientist in relativity. And it wasn't for a very long time before even Wheeler conceded that Oppenheimer had been right. And Oppenheimer, I do not think was alive when the term black hole was coined, which was like 1967.
Okay, wow.
So
late.
A half century after its mathematical discovery, John Wheeler himself, as he concedes that Oppenheimer was right, coins the term black hole in a public lecture. He's just exasperated with repeating catastrophic gravitational collapse over and over again. And he just foists this term black hole on us.
So I like the phrase mathematical discovery. That I think opens all sorts of philosophical cans of worms that I will not take us in that direction, but it's still very, very neat. One thing, though, that it really sounds like is the case, and tell me if I'm right here, is that theory, the development of theory, it really outstripped experiment.
I mean, yeah, because you can't build them in the lab. And
right.
So...
Well, actually, I have the sense that you might be able to in a place like CERN, like CERN, you might be able to make one, but it'd be really tiny. We can't make the kind that we want to observe.
Well, that would be awesome if they made one at CERN. But that speaks to the fact that black holes are fundamental particles and not just astrophysical objects. So I make astrophysical objects, they're made through natural processes, or this chair is made, but fundamental objects have a different status. And if the Large Hadron Collider could make black holes, that would be huge and revelatory for lots and lots of reasons. Probably safe. People get worried the black hole would consume everything, but actually they kind of go off like firecrackers through Hawking radiation, and they explode. Essentially, that they don't linger long enough to destroy the Earth. But no, CERN has not yet seen any black holes.
Well, an interesting analogy comes to mind for me, but where theory outstrips experiment. And the analogy is interesting because it at least tangentially involves a close friend of yours, Brian Greene, who I know was also just at Pioneer Works, which is a very cool thing to have done. It was for the Elegant Universes anniversary.
25th.
Yeah, I love that book, incidentally.
Book.
But the analogy is string theory is another case where theory has really outstripped experiment, and it's a very famous case of that and has resulted in all sorts of debates, allegations of crisis in physics. And I'm not going to ask you about string theory right now, but since you know so much about the history of black holes, what was it that took black holes from just this purely mathematical, theoretical entity to something that physicists really believed in before they had been confirmed with observation?
Absolutely. So Wheeler comes to it by using these kind of newfound computers, which allow them to study the theory more in a more in-depth way, and his own criticisms that he had volleyed against the analytic models evaporated, and he had to concede that he agreed. So that is all theoretical. But then they started to see these X-ray signals. And these X-ray signals were of the variety that we were just discussing, where there are two stars, one has died and become a black hole, and it is cannibalizing its companion, and you're seeing the material from the neighboring star splatter around the black hole, and that's all these accretion disks, and they can create jets. So basically these magnetic fields get twisted up in the material that's accreting around the black hole, and the jets are the material that's falling in, getting siphoned, literally like ray guns. Very high energy material comes spewing out, and they started to see these. Now, they couldn't resolve them like a picture. They could just collect the bright X-rays, and it was very, very small object. They could tell it was a very, very small region of space, but the power and the energy was so enormous that even if you were just thinking, I'm converting raw mass into this kind of energy, it gave you the dimensions of a black hole. It said, I have a very massive engine that's very small spatially. And people think of black holes as these monsters, big, they're actually tiny. The whole point is that they're tiny. The sun would be city-sized. A 10 solar mass black hole would be city-sized. That's staggeringly small. Even the supermassive black holes are tiny for their heft. Think the supermassive black hole at the center of the Milky Way galaxy, which is 4.5 million times the mass of the sun, is only about 18 times across, as wider than the sun. That's tiny, 18 times the width, but millions of times the mass. And so we were deducing it indirectly that must be a black hole. And that was debated for decades, actually. Started seeing these in the late 60s or early 70s. And it was debated for decades. Until it really just seemed like there was no other explanation. But the first direct evidence, the first picture we ever took of a black hole that any of us ever saw, a picture, which resolved the event horizon, where you could look at it and say, oh my gosh, there's a shadow, was 2019, was the Event Horizon Telescope. And that was a supermassive black hole in the galaxy M87. It's billions of times the mass of the sun, really heavy. It's 55 million light years away. And because, even though it's so heavy, because it's so small, it's equivalent to resolving like a piece of fruit on the moon. That's how tiny it is on the sky. And that was why it was such a technical challenge, because they're small.
Something you said really stuck out at me, and it's that you're referring to these black holes as some are very small, some are very large, and in doing so, you're referencing their radii. So I think you said the sun is if it were a black hole, it would be something like 6 kilometers across.
Yes, and that's the event horizon. By that, I mean the event horizon. There's nothing there. If you go up to that 6-kilometer region where the shadow is, there's nothing there. It's empty. Okay? It's just that there's a shadow. It would be no more dramatic than stepping into the shadow of a tree to walk into that event horizon. So when we say the radius or the diameter of a black hole, we're strictly speaking talking about the event horizon and not about any material of any kind.
And this is exactly what I wanted to ask you about, because you said earlier a black hole is more of a place than a thing, but corresponding to the event horizon is the singularity, where there is presumably just so much stuff. And presumably that's kind of what the black hole is. So that's why I wanted to ask you about why you think of the event horizon more as
I don't think of the singularity as the black hole. I think that's really important, because I know people do, and might as well dispel that. To some extent, we don't care what's going on in the interior of a black hole, because that event horizon completely separates the interior from the exterior. So as far as we're concerned, being astrophysicists, we want to be theoretical physicists. We'll talk, a little bit more about the center of the black hole. But as astrophysicists, the black hole is the event horizon. That's the important thing. We don't care what's going on in the interior. It could be a big bang on the inside. It could be as big as an entire universe inside that 6-kilometer sphere. Black holes can be bigger on the inside than they are on the outside. And we don't care. We've got no access to any of that. It's meaningless to us. So from an astrophysical standpoint, firmly, the black hole is the event horizon, not the singularity. Now let's talk about the singularity. So let's say I do form a black hole through stellar collapse. So the star is getting denser and smaller and denser, and the orbits of light are getting tighter, and more circular, and eventually it gets so small the light ring forms, and I could, in principle, make a perfect circle with light. And then the event horizon forms, where not even the light can escape and all the light begins to rain inward. It's almost like a waterfall, raining inward. The star cannot sit there anymore, because for the star to sit there at that incredibly dense point, for there to be a hard, dense star or material there, it would have to be racing outward at the speed of light just to hover. So you really have to think it's as though space-time's become like a waterfall, essentially. And so the material continues to collapse. It has to. That's what Roger Penrose showed. He showed that the formation of the event horizon was inevitable, and then the stuff of the star would be gone. It would keep falling and keep falling, and then, yes, there's this singularity predicted, but nobody believes it actually forms. So singularity says eventually all the matter reaches this catastrophic singular point where there's an infinite curvature, infinite energy, infinite density. But most people say, yeah, but you're just not doing quantum mechanics. You're not including the matter forces. And if you do, maybe some other story happens. Maybe there's a remnant. Maybe there's another big bang. Maybe it's string theory and the stuff never falls in and it's all a hologram and an illusion. Whatever is going on in there, in that interior, is really important for theory, for understanding theoretically the fundamental law. But what we mean by the black hole, it's all right there in the event horizon. And even the string theorists would say all of the information is on the horizon. It's not in the volume. And that's this idea of holography. So I think that's really, there's very few people who I think would say, oh, no, the black hole is the singularity. It's really not. It's all on the horizon.
That was great. I'd really like to get back to holography and the information paradox maybe toward the end of our discussion of black holes, but it's interesting. I hadn't heard that there was this cleft maybe where astrophysicists view the black hole as the event horizon, and maybe some theoretical physicists do not. But I have heard this in conversation before and found it quite surprising. For instance, I've said this a few times on the show. It's based on an interview on the show. I spoke with Eric Valinda, a string theorist for our listeners in Amsterdam, I believe, and he doesn't even think of the singularity as existing for some of the reasons.
No, yeah, it's been a long time since I've spoken to anybody who staunchly believes that the singularity is actually there.
Oh, really?
Not even Penrose. In Rogers, Sir Rogers' original work in like 1974 that really earned him the Nobel Prize, he says, there's a singularity is this inevitable end of this collapse, but that quantum mechanics is going to fix that.
Yeah.
He kind of brushes it away. It's not something he takes very seriously.
Yeah, given that you can just hand wave and say, okay, quantum mechanics will brush it away. I am wondering if you have any idea of what happens to all that matter after it passes the event horizon, because at least intuitively, we do want to think that it goes somewhere or something happens to it.
We definitely do. That's a big problem for the theoretical physics. It's a big issue. So what happens to the material that falls in? We know that there's this stark story. There's one very interesting thing to point out is that the material can't avoid the singularity. If we're just speaking classically, we're not worrying about what happens with quantum mechanics. We're just like, okay, let's just follow this through to what this particular mathematical description says. For anything that falls into the black hole, the singularity is actually in the future. It's not a point that can be avoided. I can't deftly just like orbit forever or just never go there. It's really become a region in the future of any infalling matter, and they're inevitably driven towards that singularity. So any solid body is going to be ripped apart and torn to shreds and broken into its fundamental bits just by the chaotic nature of how strong the curvature in space-time is in that interior. And that story, it may or may not happen to matter. Some people wonder if there's a white hole on the interior, and that when the density gets extreme enough, you actually have the equivalent of a kind of a Big Bang into a different universe, not this universe. It's not a Big Bang like inside the black hole. I might have said it that way, but I don't literally mean inside. It's as though it breaks off into a completely disjoint, causally separate universe. And you can muse about these things. I think the conversation has gotten much, much more complicated, which maybe we'll get to when we talk about holography and string theory. And I think that's where the real solutions are, that this kind of classical thinking of matter falling on a space-time is just breaking down, and we can't talk about it in that way anymore.
Fascinating. I know that you have, even though we're talking about black holes, you've done work in lots of other areas of astrophysics and theoretical physics, and one of them is cosmology. So I thought I might just ask, because I know that black holes, it doesn't seem like they'd be connected to the Big Bang or theories of how the universe began, but why is it that the two of them are often put in juxtaposition?
Well, there's similarities around the singularity precisely. So when we look at the Big Bang, what they have in common is that they are either places or events where we know that we are invoking quantum mechanics. We have to. So when is the quantum paradigm necessary? When I don't have to use a quantum paradigm to describe how the coffee is going to pour out of my coffee mug or something. I don't need quantum mechanics really for that, as you're reminded of your coffee. Mm-hmm. But I do at the Big Bang. And the reason I know that is because the energy scales are getting so high, and quantum is a high energy phenomenon. It's when the energies are so high that I am exposing microscopic wavelengths, and I'm able to probe into the very microscopic nature of the universe. And I am forced, therefore, around the Big Bang and black holes to consider quantum gravity. And we have no such thing. We have no such working tool called quantum gravity. Yet I know that it seems as though I have a space-time that I'm talking about, but I know I have to invoke quantum mechanics. And so it is the terrain on which we need to understand these things. These are the only two places, if you think space-time is a place, where we're getting clues from our calculations, from our understanding, to what lies beyond just general relativity and just quantum mechanics. Is there a quantum theory of gravity? Is it string theory? Is gravity just something that is an illusion at these high, large scales? Like solidity of a material body is just an illusion. When I look closely, will I find something completely unexpected?
I know that I'm asking you a seemingly tremendous amount of questions about something, the singularity, that you don't think actually is there. I have one more, and I've spoken to Leonard Susskind because we're both at Stanford.
He's the best.
It's easy to just get over to.
He's so fascinating and creative.
Yeah.
What a great mind.
Yeah, it's easy to get over to his office. And one thing that he comments on, I think it is in The Cosmic Landscape, but actually, since we're talking about black holes, maybe it's in The Black Hole Wars as well. But he says that people often have very harebrained, crazy ideas about what's going on in black holes, and he receives emails for this all the time. I'm sure you do too.
But I have a special folder.
Really? Okay. But one crazy idea that is actually attributed to one of the co-founders of Loop Quantum Gravity, Lee Smolin, who is a very important physicist, is that black holes are, inside of them, they spawn new universes. And there's something, I think the theory might be referred to as something like cosmological natural selection.
Oh, yeah, I think I know what you're referring to with Lee's ideas.
Yes. But I'm wondering if you think that there are any wild ideas about what could be going on in black holes that you would assign some even minimal amount of credence to.
Yeah, I think so. Lenny's ideas, they're madness. That's the thing that I think when we get these letters from people that they don't understand is we are entertaining the most counterintuitive, wild ideas, but we're not doing it just word salad. And Lenny's certainly not doing it just as word salad to be crazy. We're being forced there by these parameters. So you're asking me about the singularity. I'm not being dismissive and saying, oh, that's not real. Don't ask me about that. Quite the opposite. We're all saying, well, that's a really good clue that something else is going on. And so we have to keep heading there. Even if we think we're going to realize that the singularity is not there, it is the clue that we're chasing to some extent, saying there's something else, that has to happen. And that's what Lenny's been incredibly creative and had absolutely wild ideas like holography, which I attribute to Lenny and Tufts, the Nobel Prize winner. And they had to have these ideas because the quandaries precisely around black holes had become so restrictive and so grave. I know it sounds hard to distinguish why some of these things that people are coming up with now aren't just crazy, and why they are coming together as a coherent description. And that is sometimes in the mathematics, and sometimes it really is just in the big concepts that really are doing a lot of heavy lifting to resolve our understanding of what's going on, precisely to avoid the singularity.
I don't want to make this conversation about Lenny, but since I can tell you feel very strongly and highly about him, I think I can ask this question. I am a big fan of him. I love his books. No. I think some of his ideas are really out there and they're on the frontier. They're not substantiated by hard evidence, but I think that that's part of science. Now, philosophers in general, though, that I talk to about his work do not think so highly of him. And what I want to ask you about is what makes him, to you, such an important and inspiring physicist?
Yeah, Lenny has just a wild intuition, and he kind of just like feels it at first. It seems to me, I can't speak for what his actual inner process is, but it seems to me he has a strong intuition for something, and he will just find a way of expressing it. It's not always completely computed. It's not always follow the chalk from the beginning of a mathematical proposition to, a series of theorems. It's not always like that specifically. Maybe that's what the philosophers object to, but I'm always going to listen to what Lenny says, because he just keeps having these incredibly insightful ideas. And duality was one of them. Complementarity was one of them. Holography is another. Now they're talking about things like ER equals EPR. And even if we don't pick apart all of those things, they have been incredibly influential. And so holography, his idea on holography, it doesn't matter exactly how he initially framed it, but one way to see why there was something right there. You could, he had an intuition about something that clearly is right there. The idea of a hologram is that you encode in 2 dimensions all of the information to project the illusion of a 3-dimensional thing. And what Lenny was insisting is the black hole is a hologram because all of the information can be packed on the event horizon surface. No more information can exist in the interior of a black hole than you have on the area of the horizon. That's formally true if you calculate things like Hawking radiation. What's the entropy of the radiation? Entropy is a measure of information. The entropy scales like the area, not the volume of the black hole. So he knew something we all knew, but he said it in a really clever way. And he got everyone to go, oh, wait, yeah, that's actually something really important. So Lenny, I don't know if he would go as far as to say this now, but it drove people to consider, well, maybe there is no interior of the black hole. Forget about the singularity not existing. There's no interior. Everything, it's a hologram. Everything is just on the surface. And so if it's like some string theory model, maybe the description is as the string approaches the event horizon, it smears out over that event horizon in this stringy configuration, and it never falls through in some sense. Or there's complementary descriptions. The astronaut that falls through the event horizon thinks they fall through, but to us out here, it never fell through, and both those things are true. There's no omniscient observer who can see the conflict or the paradox. So his ideas are unbelievably profitable for the community, and even something like holography and this kind of a duality of the interior and the exterior was eventually made precise by Juan Maldacena in a specific model of a universe in a box, where he basically shows the universe in a box I can completely describe, completely accurately, in a different description, which is just the surface of the box, and the interior doesn't exist in some sense, or it's just a different description. I don't need the interior of the box. So anyway, it's just to say eventually somebody makes it precise.
I had an absolutely lovely 2-hour conversation with Juan Maldacena all about ADS-CFT, which, as you bring it up, I mean, could be by some metrics the most cited high-energy particle physics paper of all time. I
think it's the most highly cited theoretical physics paper, period, of all time.
And not only that, but it's not just that it's highly cited. Something like 4 of the top 5 most highly cited papers, like Witten's follow-up, they all have to do with holography and ADS-CFT.
Mm-hmm.
But if I were to speculate about philosophers' feelings about Lenny, I would think that the brunt of their feelings could be attributed to 3 things. 1, they are retaliating against his perceived hostility to philosophers because he's not a huge fan.
I'm a little sympathetic with that too.
I understand too. I mean, there are some good philosophers of physics, and there are
You're not going to philosophy a rocket into space.
Yes, yeah. I get it. Second, I think that they view the pushing of string theory so hard as irresponsible because they side more with Peter Voigt, who is another another colleague of yours at Columbia. And then the third thing, and this is where maybe it might be worth a few minute digression if you have any thoughts on this, is that they think that the anthropic principle and his thinking about the fine-tuning problem is just totally crazy. So philosophers agree that the fine-tuning problem is a very interesting problem, whether or not it will eventually dissolve and not be a problem at all. But I'm wondering if, fine-tuning is the sort of thing that could keep me up at night. I'm wondering if it's something that you think about at all. And if so, maybe you could explain what the problem is before you...
Well, let me just not to pose too ardent a defense of Lenny, but I don't believe Lenny will stick to something wrong. You show him something's wrong and he'll accept it. This happened with the firewall era. I don't know if you followed that, but
I know firewalls are part of your book, so would you want to talk about this for a minute before
It's a little bit tricky, but we'd have to kind of go through the whole Hawking radiation.
Maybe we'll come back to that.
We can talk about it a little bit, but essentially, the firewall crisis was one that showed that complementarity could not be, in some sense, completely respected. This idea that, if you fall in, there's nobody who can know that you fell in and also simultaneously have the point of view that you were on the outside. They actually showed that there was a real problem with some of Lenny's thinking. Let's just put it that way, just to make it simpler. And of course he accepted what they were saying. He was flipped out. He was irritated. He was grouchy. But he didn't deny what was shown to him. So I completely do not like this attitude that just because somebody has explored a possibility that they're somehow religiously adhering to it with, in some unreasonable way against all evidence to the contrary. That's not Lenny. That's not what I've seen ever. So I think if you showed him holography was wrong, he would be like, damn, like supersymmetry didn't work out so well. Bummer,
Right.
Move on.
And holography, as we've just mentioned, it remains a vital part on the frontier of theoretical physics.
And Juan Maldaceno, you said ADS-CFT, just since you have a very general audience, it's an anti-de Sitter space in the volume, and CFT, a conformal field theory on the boundary. It was a precise example of holography.
Right.
Then, boom, holography was like, it went from being Lenny's intuition and fascinating to convincing Stephen Hawking that he should capitulate, that they had found a solution to the information loss problem. So holography is done well in that sense.
Yeah, but I'm glad that you said that. But now I was curious if you thought you could pose the fine-tuning problem and say how you think about it.
There's a lot of fine-tuning problems. I suspect you're talking about the cosmological constant one.
I have all of the free parameters of the standard model all boiled into one, basically.
Yeah, let's just say that there was a hope that with string theory that there would be one model of the universe that would emerge as the only one. And that was really an ambition and a hope. And you'll hear string theorists talk about that was their hope, that there would be this one model that was the laws of fundamental physics. And instead it proliferated. You have 10 to the 500 viable string theories.
Yeah, I had an episode with Raphael Busso, who is one of the two people that came up with this number of 10 to the 500 ground states.
I forget how they calculate it. Something like 500 handles or 10 cycles around each handle or hole in the Calabi-Yau manifolds, and there's some 500 of those, and so you get 10 to the 500, something like that.
Yeah, but the number has gotten bigger.
Some people argue it's infinite. And so it went the other way. It went exactly the other way. But this is an example where I think it's absolutely silly for people to tell anybody not to think about something because we don't have an experiment yet. That's ridiculous to me. Absolutely ridiculous. So we did not foresee getting the microwave background in our, amongst pigeon droppings in New Jersey in 1967. It's a gift. It was like, wow. So to think that you can foresee what nature is going to throw our way, I think is absurd. And that all these arguments were always made. LIGO shouldn't be built because those black holes will never exist. Black holes aren't real, or they don't come in pairs, or they're not so plentiful. Well, here we are. So I'm not with the naysayers on anything. I mean, it's not my job to decide who gets what part of the financial pie. So that's a different conversation. But, go think, go out there to the frontier. I'm a huge fan of those brave pioneers, But just to say that here is a very precise example where string theorists had to change their minds. They didn't keep saying, well, we're going to find the one model. We're going to find the one model. That would be a very unscientific attitude. They said, well, what are we going to do with this? This proliferation of possible string theories or different vacua meaning, or the different conditions. Universe is always slightly different conditions, different Calabi-Yau manifolds, maybe a different cosmological constant or dark energy. Some have large ones such that we can't exist. Some have none. And what are we going to do with this? And it's not wrong to say, well, only the ones that have a kind of dark energy would be very finely tuned in some sense, but it's only in those that you have life. So here we are. That's this anthropic sort of tendency. I don't find it very satisfying. I don't professionally want to spend my very precious hours thinking specifically about that, though I have to sometimes. Sometimes we get jammed up with it. We have a really good model of dark energy, but it's really fine-tuned. I'm not happy with that. I'm not going to walk away and say, well, we just happen to be in this really fine-tuned one. On the other hand, it's not completely wrong thinking. You can't say it's wrong. That is how some things work, after all. How likely is it that it's me? I don't know what does that mean? Anyway, there's 7-8 billion people on this planet. What are the odds that I'm me? It's not a very good question. It's not a very well posed, even philosophical question. So that is just how it is sometimes. Sometimes there's 7 billion different kinds of things, and you're one specific example. And there's only one of them. There's no two exactly alike.
Yeah, I don't want to stress string theory for too long, but I'm also sympathetic to the idea that, so there's this allegation, string theory is unfalsifiable. They found that there wasn't one model, and it's like cutting off one head of a hydra and then another. They just keep popping up. But to me, that's how science works. You adapt the theory in a certain way, and that's how it develops.
The parameter space pushes your theory. Supersymmetry, which people were disappointed they didn't see at the Large Hadron Collider. And supersymmetry is the idea that for every particle that we know of, there would be a super partner such that, in fact, the cosmological constant would be zero, that there would be this perfect cancellation and this beautiful, but very elegant theory. It's almost so beautiful, it was hard to let go of, hard to believe that it wasn't true. You can't exactly just prove supersymmetry. It's disappointing. It's not where the LHC is looking, but there's a vast place of higher energies that we can't get to where it could be hiding. What can you do about it? That's life. I don't think nature cares that there's this one species on this planet that has this particular set of resources that's pissed off that supersymmetry is at a higher energy than the Large Hadron Collider. You can't say it's not true. You can't say it is true. That's just life sometimes.
Well, Janna, thank you so much for tolerating all of my probing about string theory. Now maybe would be a good time to get to the survival part of the black hole survival guide. How close could somebody get to a black hole while surviving? Could they pass through the event horizon? How do you think about it?
So this is I think black holes get a bad rap. You can actually get extremely close to a black hole and be very safe, much closer than you can get to the sun.
Really?
Right? Yeah. If you get close to the sun, you're going to incinerate. It's really quite a threatening, hostile environment. You can get very close to a black hole. Let's say it's a bare black hole. There's no accretion disk, no jets. And just to clarify for the jets, because I get this question a lot, the material being shot out of these jets, these X-ray guns, basically, is not coming from interior to the black hole. It's always coming from outside.
Right. Nothing escapes.
It never went inside the black hole and then is being shot out. It's drawing from the ambient material that's already very hot and energetic, and it's shooting it out along these magnetic beams. But so let's say there's none of that. So it's really quite safe. There's just this empty region of space-time, and there's this shadow I can't even see. Maybe I shine a flashlight on it to help me see the black hole or something. You can get incredibly close to a black hole, and it's really fine. I mean, like I said, if the black hole is 6 kilometers across, and it were the mass of the sun, even though we don't know how to make one of those, they're heavier than that, but you could be 30 kilometers out. That's really close, 30 kilometers outside the black hole and be in a very safe orbit, minding your own business. You won't get torn apart. You won't be vacuumed in. You could be like the International Space Station, make your observations and chill.
Exactly what I was thinking of.
Yeah. So, my recommendation is, first of all, go around a bigger black hole, because the bigger they are, the safer they are, surprisingly.
Why is that?
So you can think of it as that the curvature is more gradual. And the familiar example is, if I stand on a basketball, I'm very aware of its curvature. But if I stand on the Earth, I'm not so aware of its curvature. It's almost flat, and it's not a flat Earth.
Yeah.
But locally, I walk around without being toppling around because of the curvature of the Earth. So if I have a big black hole, it's sort of like a flat wall, and it's not pulling on my feet much different from my head. It's just, I'm not having these tidal problems. It's kind of like slipping, like if you were to cross the event horizon, like a little marble crossing in. It'd be a very benign experience. Sometimes people will call it no drama. There's no drama at the event horizon. It should be no more dramatic, again, than stepping into the shadow of an umbrella.
This raises the question, though, of whether you can get to the singularity then after you've passed.
Right. Well, so there's for the observer who falls inside the black hole, from outside, you think the astronaut who's falling in, it looks like their clocks are running slower and slower, because black holes don't just deform space, they deform time. And you can think of it as a rotation of space into time. It's as though all the space has been rotated, all the time has been rotated away in some sense, and the astronaut on the horizon appears to be suspended in time. But from their point of view, nothing's happened. They've just crossed right in. Okay, they just crossed right in, and it happens in the blink of an eye. But the problem is that direction towards this would-be singularity, if it exists, is in their time direction, because space and time are relative. They don't perceive that as a spatial direction. They perceive that as a time direction, and you can't avoid the future. So there's no maneuver. They can't take a crazy orbit, and there's nothing they can do to avoid that interior point, if in fact the interior of a black hole exists.
So when time is slowing down as you approach the event horizon, what's happening to space? And then also what's happening on the other side of that event horizon? Because I've heard that the spatial and temporal coordinates kind of flip.
Switch places in a way.
What does that mean? Can we visualize this?
Well, the analogy I like to give is, like, right now, my left is your right. Okay, but let's say we were facing the same way. And I did a spatial rotation. So let's say we were only interested in right hands. And I did a spatial rotation. You'd say, oh, you rotated completely away from right into left. And there is no more right. Your hand is now 100% in the left direction to you. I'd be like, oh, it's my right. It's still my right. But you would say, relative to you, I had rotated 100% into left. Okay. Space and time rotate into each other. It's not a spatial rotation. It's a space-time rotation. I can do it mathematically. I can visualize it on a map where I draw time as one of the directions as a rotation in space and time. But I can't really see it, intuitively the way I can a spatial rotation. But as you go towards the black hole, it's as though you are rotating, just like the left into right or the right into left. You are rotating time into space. And you can actually see it on a diagram. If you draw time as up and space as horizontal, that as the astronaut gets closer and closer to the event horizon, their time direction looks like 100% your space direction. And that's not odd in the example of left and right. We see that all the time, and we're used to that. We're used to the relativity of left and right. It doesn't shock us. The relativity of time is a lot harder to wrap your head around. But it is a rotation. It's just not a spatial rotation. It's a space-time rotation.
Yeah, I think that the idea of a space-time rotation is going to be very difficult for people to wrap their heads around. And I also imagine that this is a place where the formalism is a really good surrogate for what we can't do with our mind's eyes.
Yeah. And so a space-time diagram, one way to think of it is it's like a map. And we know that rules of maps are not the usual rules. I can draw a flat map of the Earth. We do it all the time. We look at flat maps of the Earth. We just understand that the rules aren't the rules of a flat map. We know that, if I go past Hawaii, I'm actually coming in the other side of the map, past Japan. And I also know that distances are deformed because it's really, I'm projecting a sphere onto a flat map. Well, it's the same thing with the space-time diagram. It's not, I'm taking a different manifold that I can't visualize, and I'm drawing it on a flat map. And so I have to learn the formalism, which are the rules of distances and space-time distances on this map to interpret it correctly. And this is an example where you need the math. If you don't have the math, you're not going to really understand it.
Well, another topic that I wanted to touch on, because you said earlier that black holes are more a place than a thing. You've said that they're more nothing than a thing.
Yes, black holes are nothing.
Mm-hmm.
That's probably the opening line of the book.
Yeah, but what I wanted to ask about was you've also said that black holes are perfect.
Yes.
And I think this is connected to the idea of black holes and their haircuts. So I'd love to hear a bit
black
about...
Black holes have no hair. Black holes are flawless and featureless, unlike anything else in the universe. So the fact that I can make, in some sense, the stunning thing about black holes is I can make them from composite things. It's more natural in some ways to think of them as a fundamental particle, because in that sense, fundamental particles are also featureless and flawless. You can't find, a quark that's slightly heavier or has a slightly different spin or has slightly different charges. It's identical to every other quark of that flavor. They're featureless. You can't make them a little fatter or give them a bump or, they're fundamental. And black holes in some sense are like that. If I go out to a black hole and I try to deform it, I put a Mount Everest on one side, and I'm like, now this is my landmark. I'll know it's my black hole, and I'm going to come back tomorrow, and I'm going to recognize it as different from all the other black holes because it's got Mount Everest on the side. It will not tolerate it. It will shake off that imperfection into gravitational waves, which are waves in the shape of space-time, and it will shake off that imperfection until it becomes flawless again, featureless. The only thing that I can use to characterize a black hole are its spin, its electric charge, and its mass. And a black hole with that spin, charge, and mass is identical to every other black hole of that spin, charge, and mass. None of them have a Mount Everest landmark on them. It's not possible. You can do it for a second, but it will get rid of it.
Am I right that for this reason, black holes have been compared to fundamental particles?
That's the way in which I think they really are.
So what is that connection there?
Well, a fundamental particle is really just a list of quantum numbers. Okay, so a fundamental particle means it has a certain mass, it has a certain electric charge. Maybe it has some other kinds of charges, baryon number or lepton number or spin or something like that. So it has a very short list of facts about it. And it is simply that collection of facts. There is no distinguishing features from one to the other. They are identical down to those numbers. And those numbers are exactly the same for every one of them. You don't have a slightly fatter electron. Now, maybe it's really a string and it's not fundamental. Still applies. If it's a string, it's the specific harmonics played on that string, the specific vibrational modes and in an abstract sense of that string. And they are absolutely indistinguishable from each other. I think that's very profound. And in that sense, black holes are also completely indistinguishable from every other black hole with that same list of, you could call them quantum numbers, mass, charge, and spin. I can't, know if it was what it was made out of. There's no history imprinted on it. There's no flaws that I can go back to and say, oh, I'm identifying something about its history. They just shed away their imperfections. And that's the no-hair theorems. The no-hair theorems meaning I can't have certain features radiating out of the black hole, and they are therefore, in some sense, perfect.
Before we transition to a slightly different topic regarding black holes, it strikes me from talking to you that not only was it immediately apparent that you're very, very passionate about education. I mean, public outreach is a big part of your career, but it's also clear that you really love black holes. And what is it about black holes that grabbed you to study them the way you do?
It really is all these things that we've been discussing, that they are somehow fundamental. So it's unlike studying anything else. Like, in some sense, you can, and I think it is a mistake. It works for some scientists, but for me, it would be a mistake. Start to hone in on one thing that's too specific, and you lose the universal picture. What is exactly the atmosphere around exactly this body and exactly this system? I mean, it's very interesting. There's a lot of work that comes out of it, but you lose the universality of it. And there's something about black holes that are universal. And that's what I mean. They're flawless. They're perfect. They're fundamental particles. They're the terrain on which we're going to understand the fundamental theory of physics. And all of these things make them that you always have to have this bird's eye view, a large, big picture view. And that's what I love about them. I'm not studying a specific brown dwarf in a specific star system exactly in that direction and this longitude and latitude on the celestial sphere. That would be too specific for me just as a personality. It would make me feel like so much was going on and I didn't have my eye on it, I feel with this topic, it is a way to keep your eye on the biggest bird's eye view all at once. And that's one of the aspects of it. And also, they're just a really superb example of relativity. When you first learn them, I mean, it really is a way to hone your skills is when you, with the formalism, is really to see if you understand these many different ways. Because of the relativity of space and time, there is no one way to look or talk about the black hole. There are views that are simply dependent on whom you ask. So the observer who falls in sees the center of the black hole as a place. You have to ask them that question. And it's really challenging to make that shift into their frame, both in terms of the mathematics and the formalism, and then to build up the intuition of what they're perceiving in this completely relative description, their space-time, versus when you ask somebody outside who has a much more familiar space-time to what we're used to, and uses a more familiar coordinate system and has a more familiar tracking of the passage of time. And they're just, they're pretty awesome.
Yeah, no, I totally agree. You said, or you mentioned brown dwarfs a few minutes ago, and I'm glad you did, because what I wanted to transition into was more black holes as astrophysical phenomena rather than Mars theoretical physical phenomena.
Yeah.
And first, can we go into more detail about how black holes form within galaxies or star systems?
Well, there's also even a big surprise, and this back to the kind of, don't think about that because, we know that there's no future in that direction. Now, I don't like that kind of attitude towards science in general. And I think this is a good example of surprises that are on the horizon. One is the supermassive black holes. They were a huge surprise. Nobody imagined black holes that were millions or billions or even trillions of times the mass of a star. And they're in every single galaxy, more or less. And we think that they're playing some very important role in terms of sculpting the history of galaxies and maybe even sculpting regions where life can emerge. And so supermassive black holes are playing some role in the emergence maybe of our species, and they're part of our story. That's a huge surprise. We don't know how those ones form. It may be that they formed directly early in the universe's history, skipping the star phase altogether, that they just directly collapse. It may be that bigger black holes form and they merge, but there doesn't seem to be enough time to make something billions of times the mass of stars. But that they, because we do see black holes merge, or we detect black hole mergers. Anyway, so those are very interesting. So nature has at least two ways to make black holes for sure. The first way is the one that we discussed, which is the death state of stars that Oppenheimer theorized about. And understanding that really, I don't know if the story is that much more in depth than the one we've already kind of given, which is when the material of the star is dense enough in the very beginning, the early stage of the star's life, it's like the critical mass of a nuclear bomb. It begins to ignite thermonuclear fusion, and that's where the elements in our bodies come from. They come from this nuclear physics, and the stars churn.
That's where it's worth stressing that everything in us comes from stars that are...
It's quite amazing.
Yeah.
The universe is mostly hydrogen and helium after the Big Bang. And when it cools down and stars begin to form, there's no carbon, oxygen. There's nothing out of which to make the material of a rocky planet or an ocean or DNA. And that's amazing. All of that material is made in the cores of stars by fusing elements through thermonuclear fusion and releasing the energy to keep the star bright and aloft and shining. And eventually it runs out of fuel. I mean, it's a lot of fuel. Stars burn a lot of fuel, but that's where, that's where all of these important elements come from. But if the star just kind of faded out, it would be locked inside the star. There'd still be no rocky planets and no whales, and no bees and stuff. So it has to explode. So it's just this wonderful gift that stars, when they're heavy enough and they've made these heavy elements, that when they run out of thermonuclear fuel, they start to collapse a little bit, but that ignites a next phase and of burning, because now you've got a more intense critical mass. And so some elements are only made in this kind of supernova explosion, because that goes off really fast. The star falls in seconds or fractions of a second, and then explodes, and it helpfully casts all those elements out into the world to be reprocessed in a second generation of stars and planetary systems. And we're definitely not first generation.
Yeah.
We couldn't be. Now that story is a wonderful story, and we kind of know that the remnant after that supernova, there'll be like a little pearl there, and often it's a neutron star. What's happened is the core that left over collapsed as far as it could before the nuclear repulsion of having jammed all of these particles together gets powerful enough to stop the collapse, and you make a neutron star. It's very nearly a black hole. A neutron star is basically like a giant nucleus, and it's a kind of an intense quantum state of superconducting matter. It's fascinating in its own right, and lots of people still study that and still trying to understand the equation of state of a neutron star. Like a thimbleful would have the mass of Mount Everest or something. That's something insane.
Yeah.
You would be liquefied on the surface because the gravitational force would be so strong you couldn't possibly stay as a coherent entity. And so very intense. And a neutron star is usually around 1.5 times the mass of the sun is the core that's left over of the neutron star. Very limited mass range. And they're about 20 kilometers across. Now, these numbers change a little bit, but there's something there, unlike the black hole. There is dense matter there. Now, if it's heavier than that, it cannot, not even the nuclear forces can resist the continued collapse. And it will go past this neutron star state. It'll go down to, let's say, the 6 to 10 kilometers, where the event horizon forms. And I don't know the state of the matter. I don't understand the state of the matter. It's beyond our understanding as a superconducting material. But it can't sit there. It just can't. You've created effectively this idea that because space and time are so relative, if I ask the person who's riding the surface of the star what it looks like to them and their coordinates, their clocks, their experience of space-time, it looks like a waterfall of space-time. And to fight this waterfall, to stay at the event horizon, which now you've kind of inscribed around you, like an archaeological record there in the space-time, you would have to be like a fish swimming against a waterfall, the Niagara. And you would have to be going at the speed of light to resist being dragged in, and you can't do that. So you get dragged down with this waterfall of space-time. That's your experience of what happens to you. At least in the beginning, you're swept along. There is no resistance. And that story is pretty solid. It's pretty sound. Now, I'm sure there's a lot of things we're still learning about neutron stars, and there's things that we'll learn, but we don't see neutron stars. There's this kind of gap where all of a sudden you start to see black holes, and their smallest ones are like 4 or 5 times the mass of the sun. Oh, really small. Like, I'm surprised they're that small. I don't really understand how they're that small. But there's a lot more that are 30 times the mass of the sun, or 60 or 80, maybe even 100. And probably those heavier ones are not coming from stars alone. They're coming from the mergers. And so they were once stars, they died, they became black holes, and they merged and they became a bigger black hole. And that merged again and became a bigger black hole. And our black hole at the center of our Milky Way will likely merge with Andromeda's black hole one day and become a real big one, a big guy. So we think that there's many histories of mergers for these big black holes. But the supermassive black holes in the first place, we don't really know how they form or where they come from. And
really,
it's a continued,
is it
area of research.
Sort of chicken and egg story with regard to galaxy formation? You don't know whether...
It is a little bit.
Okay.
There might be... Sorry, I mean to cut you off, but I assume you're going to ask which came first.
Yeah, exactly.
Black hole or the galaxy. It's probably, probably came together.
Really?
Yeah, probably. I mean, it's probably some cloud, and it starts to get some angular momentum, and then maybe the black hole. I mean, it's really not completely clear, but it probably, I would not imagine a scenario in which a black hole perfectly forms and then somehow acquires a galaxy later. I imagine that it's kind of like how the solar system formed. The sun and the planets kind of, they form together.
Yeah, that makes sense to me. Just to draw a contrast and then make it explicit about how stars form black holes, what is going to be the fate of our sun? I take it won't become a black hole, but how is it going to be different? How will it evolve differently from a star that's heavy enough to become a black hole?
Yeah, stellar evolution is pretty well understood. And so I'm learning this from my colleagues. And what they describe is there will be a similar time when the sun largely runs out of thermonuclear fuel, and it will dim, and there will be kind of a series of phases, where it kind of shrinks, and that heats it up again, and that blows it out, and then it cools, and there's you can track very well the life of stars in a kind of brightness and color diagram, and see where the star will go and how it will evolve. And we think it will end or there will at least be an important phase as a red giant, a sustained, prolonged phase as a red giant. And so maybe counterintuitively, it will be bigger spatially. It will distend. It will bloat. Although it'll be redder, it'll be cooler. That won't be good for us, because even a red, cool star is hot. And it'll vaporize the inner planets and most likely vaporize the Earth. So there's no living here in a few billion years. That's, you always wonder with climate scientists, to whom I'm very sympathetic, but I do wonder, one day this ends. One day this story ends. One day this Earth ends. We may or may not have merged with Andromeda by the time that happens. But even if we're merging with a neighboring galaxy like Andromeda, the entire solar system will go together. Whatever happens to us, if we get kicked out, if we get kicked into the other galaxy, if we get kicked around the other black hole, if we get thrown further out in the galaxy, we'll go together. It won't be like the planets go separately or something. And so, in the end, that will be the most likely fate of the Earth, is in the outer atmosphere of a red giant.
And I'm guessing it wouldn't last too long in that outer atmosphere.
Oh no, completely vaporize the Earth.
Yeah. That's quite sad.
Yeah, it's definitely a doomsday scenario. But anything happening to the sun that's drastic is a doomsday scenario for the Earth. We're not going to survive any of those phases of the sun. sun, whatever fluctuations we see from the sun, like recently there was that solar storm where a big mass ejection was lobbed our way, and millions of tons of hot material hitting the outer galactic, magnetic field of the Earth, and the northern lights traveling, and all that. All of that was very exciting. And it's really small variations. The sun's pretty stable, and our survival depends on that stability and the stability of our orbit and all of those things. You can't mess with that and get away with there's not a lot of range.
The supermassive black holes at the center of galaxies are very fascinating, massive creatures. I mean, we already touched on their cannibalism a little bit, but in keeping with our discussion of black holes as astrophysical phenomena, I'm wondering what role they play in the evolution of a galaxy, or even the structure of a galaxy.
I think a lot. I think we're starting to realize that it's a lot. A lot of this is based on simulations, and there's only so much detail that even with the current computing power, even though it's really impressive, that we can get out. But I think we're understanding a lot, and probably it has to do with this magnetic behavior. So black holes themselves, as we said, they're not shooting out the jets from interior, but they can cause mayhem in the electromagnetic environment of a lot of hot material and debris around them. And so very early on in a galaxy's evolution, those supermassive black holes were probably quasars. Quasars were called quasars as a variant of a quasi-stellar object because we didn't know what they were. Couldn't tell if it was something faint and close up or something extremely bright and very far away, and it turned out to be the latter. So these quasi-stellar objects were not stars. They were active galactic nuclei, sometimes called AGN, but they're powered by black holes. And so it's the irony that the darkest phenomena in the universe becomes the brightest phenomena in the universe, become these incredibly powerful engines. And so they're powering huge jets. Sometimes the jets are millions of light years across. They blow right out of the galaxy. And that can clear out, that can modulate and control how big the galaxy gets. It can kind of curtail the growth of the galaxy because it's blowing material out of the galaxy. And it may really play an important role on sculpting galaxies. And so the shape and size of galaxies might be a consequence of actually their active galactic nuclei. So our supermassive black hole, it's 26,000 light years away from us, was probably an active galactic nucleus once. And from some distant civilization, they're so far away, they're still getting light from our very long ago past, and they're seeing us as this bright quasar. And that would have been our very early history. Now our black hole, we call it Sag A star because it's in the direction of the constellation Sagittarius. And the A star, the star indicates that it's a black hole. So Sag A star is quiet now. Not a lot going on. Every once in a while we see something get kind of tidally disrupted, and that's very exciting. But it's not, it's nowhere near the power of a quasar right now. It's pretty quiescent.
A little bit over a year ago, there was a lot of press, this huge buildup to an announcement from an organization known as Nanograv. And I imagine that since this had to do with supermassive black holes, you'd be a great person to ask about just what Nanograv is and what it was that they discovered in black holes.
Yeah, so I'm not part of this collaboration. And I would say it's a little bit shy of a discovery. It's more an indication that they have something that could be consistent, but it's not like a smoking gun discovery, I would just say.
Do you think it was overblown?
No, I think they tried to phrase that carefully, but that's a difficult message to
for general.
Yeah, it's kind of like, well, did you discover it or not? And it's not always like that. It's within error bars consistent with a background of gravitational waves. So we were talking about this experiment known as LIGO, where I have two black holes that were formed from stars. They're maybe 10 times the mass of the sun, 60 times the mass, 30 times, something like that. And they're in orbit around each other. And as they're orbiting, they're like mallets on a drum, and they ring space-time. And they create literally waves in the shape of space-time. We call them gravitational waves. And these experiments try to record, like a musical instrument, the ringing drum of space-time from these banging mallets. That discovery came earlier than nanograv. Nanograv is trying to look at a cacophonous background. So instead of the drum having these mallets with this really predictable signal that you can hear this and go, those are black holes merging, you know? Nanograv is like this cacophonous background of supermassive black holes banging on the drum, and it's just very noisy. And so it's harder it's not detectable with the instruments that we have direct detection. So nanograv is trying to use pulsar timing. So as I have these neutron stars, which are very tight little objects, and they spin very precisely, and they make these little clocks. They could be like little lighthouses. They're very, very precise lighthouses, and we can look at these pulsars timings, and they're an array of pulsars scattered throughout the galaxy. So it's like using natural sources and saying, hey, they're making an instrument for me. I'm going to make an instrument just by looking up the naturally occurring neutron star lighthouses and their excellent pulses lighthouse timing arrays to see if they're being disturbed by a cacophonous background of this ringing space-time. They're being bounced around a little bit. And so nanograv came back with something that says that what they're detecting is consistent possibly with this cacophonous background.
We talked about black holes and the role they play in the structure and functioning of galaxies. I'm wondering if they play any particular role in the end of galaxies, because as a naive onlooker, they're very active. They're making this cacophonous gravitational wave noise, and they seem to be doing a lot of accretion. So again, as this naive pre-theoretical onlooker, I just imagine, maybe they're going to suck everything inside of them.
Well, they might. Yeah. So we're in orbit around our sun, but our entire solar system is in orbit around a supermassive black hole, Sag A star. And it's a very slow orbit. It takes a really long time. We're in kind of the outskirts of the galaxy. But we are technically falling in to Sag A star. Lots of other things are kind of keeping us from actually falling in right now. But in principle, we will spiral in, as will everything else in the galaxy. This is a time scale I don't even know the number is, so large. So far beyond the sun expiring, so far beyond colliding with Andromeda. It's just really far in the future. But if nothing else dramatic happens, if we were really just a galaxy sitting here by ourselves and nothing else was happening in the whole cosmology, everything in the galaxy would eventually fall into that black hole. That's the fate. That's what regular old mechanics says. It says things orbit. As they orbit, they lose a little bit of energy to things like gravitational waves, and they spiral in as they lose energy, like the International Space Station. If there were any atmosphere up there, we'll slowly spiral in and it'll fall into the Earth. We'll fall into this black hole. And so this was related to some of Lee Smolin's idea of natural selection. The idea was anything that will fall into black holes. And if black holes have baby universes on the inside, we will all come back. All of that material will come out in a new ecosystem. But not to get lost in that. Other things are happening in the cosmology, which is that the universe is expanding. And not only is it expanding, the expansion's getting faster and faster. And that dark energy driving this accelerated expansion of the universe, it has something to say about whether or not that's the story. That's our ultimate story. Because if the expansion gets faster, if the dark energy gets greater, we don't know if the dark energy is going to change, get stronger or weaker, evaporate away. There could be what's called a big rip, where the whole galaxy gets torn apart. We get separated from our black hole, and we don't fall in. I don't think that's the most likely scenario, but I'm not really sure what likely means in this context. We don't know. But if the dark matter kind of stays the way it is, or weakens, which is very likely that if there's something underlying this energy and it will decay, then that's our fate. we will end in a black hole. And then the black holes will evaporate by the Hawking process. But by that time, because of the expansion of the universe, there might just be like one black hole in a cosmological horizon, meaning everything else is too far away to ever see. The sky will go dark, and it will be like the universe sort of expires because nothing's happening. And there's really no compelling sense of the passage of time anymore.
Yeah. Well, this we've ended up exactly where I wanted to end with black holes. And this is going to be my last black hole question, and I think it's a fitting one. And it is, just briefly, what is Hawking radiation? What is heat death? How will the universe end? What role do black holes play in that?
Well, let's start with the Hawking radiation. So, I mean, this was another curveball, unanticipated discovery. Here, I've been telling you the event horizon is so unforgiving. I never know what's going on in the interior of a black hole. The interior might not even exist. All that matters is the event horizon. Hawking realized that if I do consider the vacuum of empty space, and I imagine in the vacuum of empty space, according to the principles of quantum mechanics, that particles can kind of be created and annihilate, and they kind of can come into existence and disappear out of existence, this kind of frothing soup that I don't notice at my big, clumsy, macroscopic scale. It sort of seems empty to me, except for where there's air, you know. The black hole can notice that. So the black hole, because of this one-way window of the event horizon, when a quantum pair is created and it wants to very quickly annihilate away, it can steal one of the pairs. And so let's say I make a particle and an antiparticle, and the event horizon, the particle is created, let's say just epsilon, tiny bit inside the event horizon, and the antiparticle's just outside the event horizon. Now they're separated. They can't go back to the vacuum anymore because they don't have the properties. They're separated. I can't neutralize this antiparticle and give it the property of nothingness of the vacuum. So it's stuck. It exists now. It's in reality. That sounds crazy, but it's a very solid result. Nobody disputes Hawking's calculation. What happens is the black hole actually gets lighter in the process, and the particle on the outside escapes away as radiation. So the reason why it's worth going into that story and not just saying, oh, the black hole radiates and evaporates away, is because that makes it sound like stuff's coming from the inside. It's imperative to understand that the material is stolen from nothingness of the vacuum. It is not originating from the stuff that fell in, the star, let's say, that formed it. And that's really tricky because now the black hole's evaporating away, but nothing made it out of the event horizon. And that seems like a very terrible conflict. And it ushered in this famous information loss paradox that drove Lenny crazy, that made him think about holography and duality and complementarity, and made Juan Maldacena think about this. Now, however complicated the story is, because we don't have that much time left, I can say the reason why Juan Maldacena's result was so important for the black hole information loss paradox. So here's the problem. Quantum mechanics does not want any information to disappear from the universe. That's nonsensical. Quantum mechanics is rigidly built to forbid such things. Information is conserved. So whatever went into the black hole, once the event horizon's yanked up, it better be there or have come out. It can't just have fallen out of the universe. And the Hawking radiation doesn't give you a way to do that. That's obvious. It's not coming from inside. And so this was a huge crisis for theoretical physics. Now, the reason Juan Maldacena's result kind of tells you it's not a problem, even though it doesn't exactly show you how to do it yet. It says that even if I have a universe in a box with black holes that evaporate, whose event horizons get pulled up, physicists running around, oh my God, what happened to the information? They might not be able to solve the problem, but basically Juan's conclusion is it doesn't exist because I can tell you that's equivalent to a quantum field theory on the boundary of the box that has no gravity, no black holes, no information loss paradox. There is no information loss because these are the same description in different languages. And if you can't lose information on the quantum field theory on the boundary, there's just pure quantum mechanics, absolute information preserving, then even though I don't understand exactly how to get the information out, it's going to come out. Okay. And so that's when Hawking was like, all right, I capitulate.
Well, exit black holes and enter
Mic drop.
enter Pioneer Works. So I understand that you're the director of sciences there, but first, what is Pioneer Works? What do you do there? What can people do there?
So Pioneer Works is a very influential cultural center. I think it's the most exciting experiment going on in culture in New York City, and that's saying a lot. It is a cultural center where we have artist residencies, music residencies, very occasionally a scientist in residence. We do big exhibitions and lots of conversations. So it's very much a vibrant place. It's a place of process. It's not a museum with a permanent collection or anything like that. It is really this old factory, former ironworks factory in Red Hook, Brooklyn. And it's just a very active space. You can open the calendar and see a variety of things going on different nights and different events. So Pioneer is just, it's a cultural center. It's very vibrant, very energetic. It's really about community and keeping conversation going. And I think that what we're doing that's so exciting is we really believe that in this foundation, there are pillars of art and science. And I don't know any other place that actually really does have science as a foundational pillar alongside art. We kept saying the founder artist, Dustin Yellen, and the founding artistic director, Gabriel Florence, and I founded Sciences, who are like a little triad. We kept saying, we're building the world we want to live in, and because it doesn't exist yet. I don't have a place to go to like that. I want to go to a place like that. Some nights we have string theorist Brian Greene. We've had Nobel Prize winner Kip Thorne, Roger Penrose, Richard Dawkins. They've all come. Ray Weiss, really within like a couple of weeks of him getting the Nobel Prize. I suspected he was going to get it. So I was like, please come in October.
That's good. That's good.
And, famous biologist, George Church. I mean, the great minds, amazing. And they come and they're talking about, we like to get to the point where we're talking about things just outside of our range of understanding, and that's the fun, like we've done today. You get to the point where you don't 100% know the answer. And that's the thrilling space for scientists. And the audiences are incredibly enthusiastic. And we get hundreds, 800 people will come to our events. It was a surprise to us, I'm going to say. And it's, people come early, they see the art exhibitions, and sometimes there's tension between the event we're doing in science versus, the exhibition. We're finding some friction between. There was some interesting intersections. Sometimes we host conversations right inside the exhibit itself. So they're real happening. Astronomers come out and bring telescopes, and we have viewing in the garden. And it's our big ambition to build New York City's first public observatory on the top. And this is, this is, I don't know if you know the film Fitzcarraldo by Werner Herzog. Werner Herzog, great, iconic director. One of his craziest and most beloved films, the main character drags an opera blaring steamboat through the Amazon jungle to bring culture, to all. And I feel like we're kind of doing this crazy ambition of hoisting this observatory on the top of this, late 1800s building. And you'll be able to see the observatory from certain points in Manhattan. And if you're on the ferry coming across, so it'll impact the skyline. And I'm really excited about what it means in terms of continuity of thinking about these old buildings and this old technology of observatories and astronomy, and looking into the past by looking into space through the lens of like contemporary culture, and to like kind of like really imagine our future.
Yeah, as you know, I wish I could go this trip, but it's just too short. But still, everything I've heard from you, that guest list, the pictures I've seen, it's also just an extraordinarily beautiful space.
Very beautiful.
So it does seem like something very cool that's going on in public sciences and arts. But, I'm about to be very cheesy, which I hope you'll permit me. But
Yes.
we talked about how black holes are perfect, and I think that I chose the perfect guest for the black hole episode. So thank you so much for doing this with me, Janna.
Robbins.
Thank
you so much for having me. It's a lot of fun.